Okay, good evening, everybody. Again, my name is Saida Said, and I am re- one of the teaching assistants for this course. And this is the ninth interactive session. In the last interactive session, we did some questions on consolidation, some general questions on consolidation, and we also did some questions on primary and secondary settlement. So in week 9 also consolidation has been covered. So we will be doing some more questions on consolidation, and generally we might be talking about the solution to the equation for consolidation, okay, and time rate of consolidation. First of all, let me discuss a little bit about uh, the consolidation procedure. In the previous class, I already discussed like how the consolidation test is done. But in this class, in this session, we will be discussing exactly what consolidation is. So you see, okay. So there is a spring analogy that we usually talk about when we talk about consolidation. Let us say that we have a vessel, and in this vessel we have these layers of a porous material. We can imagine it as like that wooden cork kind of material that is used as stopper sometimes for bottles. Okay, so we have a structure like this, and let us assume that this is connected to the next layer through springs. Okay, now these can be very stiff springs, or these can be like less stiff springs. So here what we are doing is we are trying to visualize what we are trying to do is we are trying to uh, simulate the behavior of soil in this way. Like we this is the pore space, and this is the structure of soil, and this porous material here we have simulated to simulate that it has a limiting permeability. The soil has a limiting permeability. So if the pores pores are completely filled with water, let us say that it is in a saturated condition. Okay, now the pores are completely filled with water. It is saturated. And now if I place a load, let us say a uniformly distributed load over this, you see these springs, these will act as resistance, they will act as like plungers. But at time t equals to 0, like at the beginning of the loading, at the beginning of the loading, since at t is equal to 0, the deformation in the springs is 0. Like there has not been any time for deformation to happen. All of this load that I have applied, the excess load, is carried by the water. Okay. So at time t equals to 0, all our load that we have applied, which is delta sigma, this will be carried by the excess water pressure. Excess water pressure is in excess to already the pore water pressure being uh, exerted by the water present. Now this will be, so our total water pore water pressure will become U plus U naught plus delta UE, and our loading, actually I should write it like this. So our loading is delta sigma dash, and our pore water pressure before loading, let me write, loading is 0, pore water pressure is 0, no, pore water pressure is U naught, and effective stress is equivalent to sigma naught. Okay, so this is before loading. Okay, so this is, one second. Okay, so this is before loading, before we have applied any loading in this system. The pore water pressure will be U naught, effective stress will be sigma naught at any point. And now at loading, the loading I have applied is delta sigma dash. Okay, so the pore water pressure, the whole of this loading will be taken by the water itself at T is equivalent to 0. So pore water pressure will become U naught plus delta UE, which is equivalent to delta sigma dash at T is equivalent to 0. And effective stress will not change. Will change, but because U is changing, but not the sigma part, not the stress, total stress. Uh, Let me say if this was sigma naught dash minus delta UE. Okay, so as time goes on, the springs they will start to compress. As these springs compress, water will flow out of the pores of this material. Okay, water will flow out of the pores of this material, and you see the whole structure will start deforming and there will be a consolidation. Now the height will be reduced. Consolidation is taking place. And how is the consolidation taking place? Consolidation is taking place by the escape of water through the pores and reduction in the pore space. But we have to know that how this comes out to be is that initially all the load is taken by the water, and then with time, as time tends to infinity, the excess pore water pressure will tend to zero, and our change in effective stress will tend to delta P, whatever stress we have given, delta sigma naught. Okay, so if we draw it graphically, let's draw it graphically. Actually, let me take another page now. So at T equals 0, we will have a total stress increase. We'll have a pore water pressure increase. And we have an effective stress increase. So at T equal 0, the total stress increase will be equivalent to our total loading. Total load is delta sigma, excess load that we have applied. So this is our sample, and we have applied a loading delta sigma to it, and this is the height of the sample. Let us say that this axis gives us the depth of the sample, and this gives us the stress. Okay, the change in stress. So throughout the depth, the total stress will be same, but at T equal to 0, the change in pore water pressure throughout the space will be same. It will be maximum, which will be equivalent to delta U equivalent to delta sigma. Here you have to understand, and as I said, that initially zero stress is borne by the soil structure. All the stress is borne by the pore water. Now, initially at T equal to 0, there will be no change in effective stress. There will be a change in effective in pore water pressure equivalent to delta U, is equivalent to delta sigma, and as a result, you know total stress is equivalent to sigma this plus this. So the total change will be this total delta sigma. This is delta U. This is delta sigma dash. Okay, but excuse me. Why throughout the depth we will have same? You see, here throughout the depth we will have same water pressure, because as the pores are interconnected, low transfer mechanism, water, like the whole phase will bear the weight, not only the top surface or the bottom surface. All the water channels throughout this, they will collectively bear the weight delta sigma. Now, as time is equivalent to t, like at any time, yes, yes, we can consolidate it, but in that case, what we have to do is we have to consider uh, a, it's called suction pressure. Uh, you see, we write sigma is equivalent to sigma effective plus pore water pressure, isn't it? Now, this pore water pressure we take due to the water in the pores. When you have, that is a total different branch of unsaturated soil mechanics. In unsaturated soil mechanics, we have two components here. This will be sigma is equivalent to sigma dash plus um, the pressure due to water plus uh, this is chi, like you kind of factorize it based on the saturation, like how much of the saturation is equivalent to volume of water divided by volume of voids. That is, in a three uh, phase space, you have a solid here, you have water, and you have air. So saturation tells us how much of the void is filled with water. Okay, so we will take a pressure for, because this is basically pressure. This is pressure, this is pressure. We will take pressure due to water, multiply it with saturation, because multiply it with saturation because that portion is filled with water. And then we will take suction pressure, multiply it with 1 minus saturation, for example. Are you understanding what I'm saying? Uh, See, that is what I'm saying is that is a different concept of totally unsaturated soil mechanics, in which we have to take some more constraints. We take, for example, I'll have to refer the book, but for simplicity, I will mention that we will take total stress is equivalent to effective stress plus stress due to pore water pressure plus stress due to pore air. Okay, so pore water pressure, we take as U, but pore air we will take as um, this is chi times. I have to refer to a book. Just one moment, because I am not. Yes, please. Yes, please. Yes, please. Let me check the question. Yeah, you can repeat the question. Okay. 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 So first you will, yeah, first you will calculate. You should see. I will tell you. When we talk about stresses on a point in continuum mechanics, when we talk about stresses in a point, for example, you have a body and you take a point and you take a slice here. Okay. When we talk about principal stresses, we say that there is no shear component. Yeah, in that plane. So when I cut through this, it is not necessary that the slice I have taken, that the section I have taken will not have a shear component. But in continuum mechanics, it is always possible to rotate this plane in such a way that there is zero shear stress. Like this is what we are doing. Like if we are taking this plane and then we rotate the plane, something like this, up till a point where we will get shear zero. So we will have those principal sigma 1, sigma 2, sigma 3. Okay. So you have been asked to, what was it again? Radius of the Mohr circle. Mohr circle specifically, you do not plot the Mohr circle between sigma x and sigma y. You only plot it between sigma 1 and sigma 3. So first you have to do is that you have to calculate the sigma 1 and sigma 3 for this. Okay. Yeah. Sorry. Yeah, yeah. A normal stress and shear stress, but in the principal plane. Okay. So this will be the principal direction. This will be the principal direction. Because then only you can use the pole method. Okay. So you will calculate the sigma 1 and sigma 3 for this, and then you will have you can calculate the radius as sigma 1 plus sigma 3 over 2, and you can calculate the this is minus center as sigma 1 minus sigma 3 by 2. This will be sigma 1, this will be sigma 3, isn't it? That is what you are not understanding, sir. See, listen to me again. I will tell you the procedure exactly what goes into it when we talk about stresses in case of porous materials. Okay. For example, uh, let us talk about the applied part of this thing. You have an embankment. Okay. I'll give you a visual idea of this. I am modeling this embankment in a finite element method software, in which I have divided the embankment into a number of small regions. Now, for each region, if I'm to calculate the effective stresses and the loads on this embankment, for each region, I will make the calculation for, I will take this is the region. Okay. So this region will not specifically be only sigma 3 and sigma 1, isn't it? But it will have sigma x, it will have sigma y, it will have tau xy, tau y, isn't it? It will have a stress tensor, Cauchy stress tensor it is called, of 3 cross 3 matrix. which is populated like this, and tau y z. Okay, but because this is just one point, this was the first step. I got this Cauchy stress tensor from this. More in continuum mechanics, what we do is we translate the axes. The same, if I was looking at it by like this was my axis, x and y. Now I'm going to transform the axis. I'm going to rotate it. And as I rotate it, there will be a, configuration, because you see here the value for this depends on your axis. This is dependent on your axis. If you had taken something else, your values for sigma x, sigma y, sigma z would have been different if you had taken a different plane. So yeah, so to eliminate that effect, what we do is there is only one principle. At every point, you can rotate the axis such that you can get your principal stresses sigma 1, sigma 2, sigma 3, and then shear stresses will be 0. That does not mean that there are no shear stresses acting on the body. It just means that there are no shear stresses acting on this particular plane along which you have now made the cross section. And then when you draw the Mohr circle, sigma n and tau, you don't need to worry about shear stress. See, you draw this Mohr circle and then you draw the envelope and then you say that it is failing here. Then how it has a tau here if there was no shear stress? Yes, some other coordinate system. Yeah. Um, can you give me the values? One second. Uh, okay, give me the values. No, no, give me the sigma values. Okay, okay. You can give the options. Hmm? Square root of. Hmm? 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 Hmm. Okay. So, can you tell me the equation for sigma principal stresses? Sigma 1 comma 3 is equal to sigma x. Hmm. Can you refer to the book and tell me the exact equation? No, it is sigma x plus sigma y by 2 plus minus How is it possible means? Y minus sigma x square over 2 plus tau xy square. Okay. So radius you are asking. The radius you know is sigma 1 minus sigma 3 by 2, isn't it? So let's do that. Sigma 1 is sigma x plus sigma y over 2 plus square root of sigma x minus sigma y square over 2 plus tau xy square. And sigma 3 is sigma x plus sigma y over 2 minus square root of sigma x minus sigma y by 2 square plus tau xy square. And we will subtract this. This will be subtract. This will be subtracted. This will go. This will go. And this will be minus minus plus. We will get sigma 1 minus sigma 3 equals 2 times square root of sigma x minus sigma y square over 2 plus tau xy square, isn't it? And the radius is sigma 1 minus sigma 3 by 2. So it will go here. So this will be the answer, the first one. This third, C, third one. Yeah, I will talk. If you have any questions on the solution, you can put it in the discussion forum. If you think that the question is wrong, answer the solution is wrong, you can put it in the discussion forum. Okay. Yeah, I will advise you to talk to them on the discussion forum. Okay. Oh, okay, okay. Yeah, I will do that. Yeah. Your assignment score will be fine. Yeah, sure. Yeah, okay. Uh, hmm, 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 okay. So give me 1 minute. I want to just check one thing. Um, as far as I know, the angle of friction and oblique maximum of 1 second. I'm sorry. Just 1 minute. Can I hold for a moment? Just I have to take this call. Just okay. I'm sorry. So, what is your doubt in this question? Um, so, see, there is a difference between the angle of obliquity and angle of internal friction. Okay. So, angle of obliquity you can think as yeah, at any time. So the you can say the on the maximum on the plane for the maximum shear stress. Okay, the angle will be um, the final. I think the solution for this is that the soil takes uh, the failure of soil takes when angle of obliquity is maximum, because angle of obliquity, as you are saying, it is the, see, you said that it is the angle between the normal and the shear stress, re- resultant and the shear, and the, so this, for example, when we talk when we talk about inclined force, we have a normal here and movement is taking place here. This will be the tangential. For example, we are um, placing a load here, P, there will be a normal stress, and the block is trying to move downward, so there will be a tangential stress. No? So that based on this, there will be a resultant. And for example, this is the angle of obliquity. This resultant will change its direction based on the magnitudes of Ts and sigma n, won't it? If sigma n is increasing from 0 to sigma n, for example, this angle will keep on increasing, isn't it? It will not be constant. Are you? So, for for example, you are gradually loading. This is sigma n, this is tau s, and this is sigma n. Okay. So when your resultant, when your sigma n is low, you may have like resultant is changing the angle, isn't it? As the loading is increasing up to a point where this over this friction is overcome. We call it the limiting friction angle. We used to call it, isn't it? We used to call it the limiting friction angle. Above that, the resultant will be here. Above that, this will simply start moving. So this maximum friction angle before the movement takes place used to be the limiting case. And that is the same here in soil also. Unless and until that limit is not crossed, your friction will not be mobilized. You understand? And that limit is the max angle of maximum obliquity. Now yeah, I have to cross check it with one of my colleagues because I am a little bit, I have a little bit doubt about the uh, angle of obliquity and like the exact definition. I know for one fact that between phi and angle of obliquity, one of them means the maximum angle before failure, and one of them is just the resultant between sigma n and the angle between the resultant and sigma n. But which is which, I have to ask because I'm getting little doubtful about the definition of the. Do you understand what I'm saying? Like the concept is same as I told you, but I just need to re-verify, was it the angle of obliquity which was changing or was it phi which was changing? But the concept is same. Okay. If it is phi which is changing, then it will be 3. And if it is angle of obliquity which is changing, then it will be 1. Okay. Yes, yes. Yes, yes, yes. I'll tell you. Just a moment. My this stop working now. Just Okay. Sorry, this just crashed. Can you please repeat the question? I'm a little confused. Okay. Where was it zero for NC soil? Where was it zero? NC soil or clay? See, what I am imagining right now is, as we talked about the pre-consolidation pressure. So, as we load a soil when it is over consolidated, which means that it has, like, if this is a fresh till, like freshly placed soil just out of the truck, and you start stomping on it, it will show very high reduction in volume, won't it? And if you have all, huh? Yeah, yeah, this is NC. But now you have already damped the soil with a load P. And if you want to tamp it with another load, you'll have, yeah, yeah. So the structure of soil here is flocculated, and the structure here is dispersed. Okay, as far as I can like think about it, I will still cross check on this, but morely because this dispersed structure is face to face, this will provide greater cohesion as compared to the flocculated structure. But excuse me, I have to uh, uh, just give me a moment. Okay, I will just check the book. But is this making any sense to you? Okay, okay, okay. Yeah. But where it was mentioned that NC soil has a zero cohesion. Okay, okay, okay. Okay, okay, okay. I will just mention. I'll tell you. Uh, just a moment. I think, okay, so it's written here that the C dash for sand and inorganic silt is 0. For normally consolidated clays, C dash can be approximated at 0. Uh, can you see my screen? This is BM DAS. Okay, so shear strength based on total stress. Okay, the values of C dash for sand and inorganic silt is 0. For normally consolidated clays, C dash can be approximated at 0. All consolidated clays have values C dash that are greater than 0. The angle of friction is sometimes referred to as drain friction, angle of friction. Typical for this is given this, but I don't think there is a explanation given. Let me check. So based on 12.2, second profile contact pressure. Actually, let's check in the environment section. This is the ambient cohesion. No, I don't think. That is one thing that comes to my mind. But to be perfectly honest, I did not know that. I had not come across that before this course. And when I came across it, I did not think much of it. But I will look into this. This is a very interesting question. I will look into it. But uh, one thing that came to my mind is the difference between over consolidated and normally consolidated is definitely in only the structure of the soil. While this is dispersed, that's flocculated. That can be one of the reasons for lower cohesion. But if you think of it, if you have a normally consolidated clay, how much cohesion will it show? It is easily breakable, is it? It is easily shared when you have NC clay, as compared to when you have OC clay, it is kind of stiffer and it actually shows good amount of strength, isn't it? Yeah. One more thing can be there. when we talk about C dash and phi dash, uh, this is not exactly. See, when we're talking about C dash and phi dash, we are not exactly talking about any fundamental property of soil. We are talking about the property of a soil given some conditions. So we will take C dash, we will take phi dash. There will be a condition that this is a drained test. This is a drained test. Then there will be a condition. NC, it will be different. OC, it will be different. So when we move on towards critical state soil mechanics, and we talk about the critical angle and these advanced failure criteria, more these modified Gamble and everything. We talk about a critical angle up till which, for example, you have an NC clay, it will show high volume reduction, while at with sharing, and OC clay will show an increase in volume with sharing. Okay, and they will try to reach a uh, equilibrium void ratio. This is the critical void ratio. Okay, and in its critical state, the friction angle is the critical friction angle. Okay, so here we are talking about the cohesion, isn't it? If we talk about cohesion in this state, it may be something like it may have a cohesion. Your OC, your NC clay may have a cohesion component at critical state, but what it is trying to say is that cohesion and friction angle that we have uh, defined in classical soil mechanics is not a fundamental property, and it depends on NC and OC. And if you say that the NC soil does not have cohesion, it means that the same soil, when it becomes OC, it will have cohesion. It will be the same soil. It's not the fundamental property of the soil. Do you understand? Yeah. It will depend on the state of the soil. It's saying that the same soil, when you apply loading to it and it comes in the OC form, the same soil will show cohesion. So it does not mean that the soil, which is clay, does not have cohesion. It just means that in that state, NC state, the definition of cohesion that we have given will be zero. Do you understand what I'm saying? Okay, so you can tell them, no, no, no. You don't talk about critical state of soil mechanics. You tell them when we talk about residual, uh, you tell them that in classical soil mechanics, the C and phi that we calculate are conditional and they depend upon the conditions. When we are saying that NC soil will have C equals to 0, it does not mean that this clay does not have a cohesion. It means that the clay in this particular state will show the cohesion will be 0, but the same clay, as soon as you pound on it and we make it OC, the same clay will show cohesion. So your question was, at the end of the day, it is clay, so why it does not have cohesion? Isn't it? It does have cohesion, but not in this state. Okay. Okay. Yes, please. I'm afraid of your questions now. Yeah. Okay. Okay. During the sample? Yeah, yeah. Yes. 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 No, it will not fail. No, it will. It no, it will not fail. It will. It can reach a plastic state where it it can reach a critical state, but it because you think of it like this. Uh, you have a body and you are applying same force in all directions. The most you can do is you can reduce the volume to it. This configuration of forces will never create a shear force for it to fail. And by failure, what we mean is that it will, it sh they should move, there should be relative movement. But when you provide volumetric strain only, this is in such an equilibrium. So in a real case, it may fail because I don't think that we can ensure that our instruments are so accurate that there is zero shear present, that there cannot be a single point of shear on the body. But theoretically, you can say, because if there is only a little bit of deviation from this axis of the load, a little bit even, that human error can do, na? So in reality, it may fail, but theoretically, by only providing volumetric shear, you cannot make this fail by providing volumetric strain, you cannot make this fail in shear because there is no component of force in that direction so that the body or the particles of the body will move relative to each other. Do you understand what I'm saying? See, you understand? For shear to take place, there should be an imbalance of forces. And when these are perfectly balanced in all sides, how can an imba it there needs to be an imbalance of forces for shear to take place. And by stating that this is a hydrostatic loading or this is a purely volumetric loading, you are saying that there is no imbalance of loading. So theoretically speaking, there cannot be a shear failure. You understand? Yeah. Please, thank you very much. Six. Can you ask the students that are taking this course to mail me on this email ID that I'm writing right now? Just ask them to mail me on this ID c.iitr.ac.in. They can mail me about any doubt as well, and they can mail me about this problem in assignments. Yes, yes. Okay, thank you very much for engaging in class. It was a really good experience because usually people don't come to class, come to my class, and I end up talking to myself for the whole time. So the interaction was very nice. Thank you. Okay. Yeah, yeah, yeah. No, definitely you can mail me. Okay. Okay. So let's move on forward with this question, with this explanation that we were talking about. Mm, okay. So as I was saying, that as time progresses, you see the total stress will not change. The total stress will remain as it was entirely, but the pore water pressure now will start decreasing. And where it will decrease? See, for the pore water pressure to dissipate, water has to leave this. Uh, so at the ends of the sample for 1D, for example, if you are talking about one-dimensional consolidation, water will start leaving from here. Water will start leaving from here, and here the excess pore water pressure will become zero. So at the ends, the delta sigma will decrease, and at the center, it is yet to decrease because water has not escaped these pores here. Okay. And as for sigma effective, at the ends, one second. Okay. So at the end, let's say this is the if you have at t this now delta u will be less than delta sigma, isn't it? And here this will be the pore water pressure, which has become zero at the ends, and as totally converse to it, effective stress will have become high, equal to delta sigma at the ends, and as water is leaving the middle zones of the layer, effective stress will keep on increasing, and then finally at this was at t equals 0, we had Okay, so this was the total stress. The total stress will always remain same because when half of it is taken by water, other half is taken by effective stress and vice versa. But the total stress will always remain same. So at time 0, you will have this. At time t greater than 0, you will have this. And at time t tends to infinity, you will have this as 0. And you have this as 0 at t equals to 0. And this is just the inverse here. And this will be completely transferred delta sigma here. Okay, delta u equals to 0 and delta sigma dash equals delta p, whatever force that we have applied, excess. Okay, and delta u will be equivalent to p. Here delta u will be less than p. Yeah, delta sigma dash will be 0 and delta sigma dash will be greater than 0. Okay, so this is how the pore water pressure inside the soil sample is changing with time. And in fact, if we uh, plot an isochrone, isochrone is a plot that gives us the value of a quantity at the same time. So what we do is we draw an isochrone for the pore water pressure in a soil. Okay, so this will be clay, and we have these piezometric lines. We have these piezometers. If we attach these piezometers, let's say that your water level initially was here, okay, and you applied a load at time t equals to 0. So before applying the load, your all the piezometers would read up to here. This would be, remember, in a no flow condition. If the water was flowing, then the piezometers would have some other readings. Okay. So at the instant that the water, that the load is given, this water will rise suddenly towards here at t equal to 0. This will be the isochrone. All the watt piezometers will increase up to here. At t greater than 0, this piezometer and this piezometer will not show any excess pore water pressure. See, this is the excess pore water pressure. This is the normal pore water pressure up till here. This is the U. This is the excess, delta UE. and this will be equal to delta sigma at t equal to 0. And for t greater than 0, what will happen is that these boundary piezometers will go down and you will have piezometric line like this. So this will be the isochrone at any time, will be the path followed by the heights of piezometers attached to this sample at any given time. That is the concept of consolidation. Now let us look a little bit into the uh, let's look a little bit into the solution for the equation of consolidation. Okay, so let's talk about the equation a bit. The derivation of the equation you must be already knowing how we derive, so I will not go over to that. But let's talk just a little bit. I'll not go into depth with this because this requires some mathematical tools like Fourier transform and like for its solution. But as you know, your equation is del square u over del x square is equal to Cv times del u by del t. So Cv is del u over del t equals Cv times del square u over del x square. So you see this is a partial differential equation, and why we are saying that this is a partial differential equation, because it is varying in two domains. It is varying in time domain as well as in the space domain. And if you want to write it in three dimensions, then you write del u by del t equals Cv del square u by del x square plus del square u by del y square plus del square u by del z square. Or you can write in cylindrical coordinates, because that is what you do in radial consolidation. So what it is saying is that rate of change with time is dependent on the like um, variation of uh, this in space, but variation of pore water in space. But let us, for example, assume that this is a homogeneous material and there is no there is no difference in x, y, z directions. Let's say it's an isotropic material for argument's sake. Let's say it's an isotropic material. Now, now you have this and this direction x. Okay, and you have as we drew that you have for water pressure distribution like this. Okay, xs. So the rate of change of pore water pressure, total pore water pressure, is a function of the rate of change with respect to, like, the second derivative with respect to x. Like, it is a function of this, the du by dt is a function of this. And you solve this kind of equation mathematically, and you will get the solution. First of all, you need initial conditions for this, and you need boundary conditions. So the boundary conditions are z is equal to 0 at u equals to 0. Okay, at t equals to 0 and z is equal to 0. Let's say here this is z equal 0. No, this is z equal 0 and this is z equal h. And let us say that they are freely draining on both ends. Let's call this h. Let's call this h. Let's call this 2h. So the initial condition will be at t equals to 0 and at z equals to 0, u equals 0. U equals u naught, not 0. But not at z equal to 0. At all points, u is u naught at t equals to 0. This is the first initial condition. Then you have boundary conditions. At t is equal to whatever, z equals to 0, you will have u equals to 0. And at z is equal to 2h, you will have u equals to 0 because here is where the water is leaving. So these are the conditions you impose. And then what you do is you calculate three factors. You calculate three factors: PV, UZ, and H. The PV is the time factor. This is CV T over H square. UZ is the degree of consolidation. It tells you the how much consolidation over how much consolidation has already taken place at a time t, and H is simply the depth factor. It is 1 h is equal to h for it becomes on it depends on the number of drainage spaces, and then you take the time date. Average degree of consolidation is equal to 1 minus 1 by like degree of consolidation. Then you can actually have these charts, like you calculate TV, you calculate UZ, and then you have these charts. This is Z by H. You have these charts. On the Z direction you will have UZ. On the X direction you will have H, which is Z by H drainage. Let's call it drainage. And then you will have these charts for different TV. For example, my TV for TV equals to 0 is here. TV equals 0.1, 0.2, 0.3, 0.4, like this. Okay. And then TV equals 1. For example, when I calculate CV, what will CV depend on? What will TV depend on? It will depend on the CV and the H of the soil. Okay. What is the thickness of the layer and what is the permeability? Because CV is basically uh, K over mv gamma w. This is the compressibility, this is the permeability, and CV you will get. So On the permeability of the soil and the thickness of the soil, you will get TV. And if you have a high TV, you see there will be uh, what we can say higher degree of like it will take less time for consolidation because at whatever height of the sample you want to calculate, you have a layer of height h, and at z you want to calculate. At z is equal to whatever you want to calculate, you take that here. Okay. Then TV you calculate it based on at what time you want to calculate. Okay. You take that here. And then, for example, let us suppose h is equal to 0.4 and TV is equal to 0.1. So TV will be this, h will be 0.4 somewhere here. We can calculate the uz. How much consolidation has taken place? uz is from 0 to 1. You see, higher the TV, greater the consolidation, lower the consolidation time. Okay. Okay. So that is it for today, I think. Yes. Hopefully, let us meet in the next class with the earth pressure theory. Thank you very much, everybody.